Welcome back. If you're here, you're probably pretty focused on mastering the systems that literally run our digital world. Today, we're diving into an essential Linux networking guide. We've put together a really comprehensive explainer on a topic that is just absolutely foundational to modern computing. We're going to take a journey together, starting from the absolute basics of local connections, and we'll work our way all the way up to enterprise cloud scale. And just to put the sheer scale of this into perspective right out of the gate, consider this. According to IBM, an astounding 96% of the top 1 million web servers in the world are powered by Linux. I mean, think about that for a second. The vast majority of the internet you interact with every single day relies on this specific operating system to connect, to share data, and to just function. IBM actually hit the nail on the head when they said Linux networking provides a flexible and secure networking infrastructure that many enterprises rely on for their core business applications. So this isn't just about tinkering on a personal computer at home. Understanding how Linux handles networks means understanding the very backbone of global enterprise IT. Mastering these skills is absolutely crucial for any IT professional. Okay, so here's our roadmap for this explainer. We've got 1. The Linux networking powerhouse. 2. Core concepts. 3. Building a basic network. 4. Managing interfaces. 5. Routing and troubleshooting. And finally, 6. The enterprise advantage. Let's start with Section 1, the Linux networking powerhouse. Before we get into the weeds with the command line, we really need a macro view. According to IBM, Linux networking relies on 4 core pillars. First up is configuration, right? That dictates how your network interfaces and routing are actually set up to share traffic. Then you have management, which is all the tools you use to monitor performance and resolve connectivity issues. Third is security, and that involves deploying robust firewalls and access controls to protect your data. And finally, virtualization. This is where you use abstraction to efficiently share resources, like treating a piece of software as if it were a physical network switch or router. Moving right along to Section 2, core concepts and protocols. To really grasp those 4 pillars, we have to establish the foundational rules that let these computers actually talk to each other. And that brings us to the bedrock of modern networking, TCP/IP. So Transmission Control Protocol, or TCP, provides the means of transport. It's basically the rules for how data is packaged up and sent. Internet Protocol, or IP, provides the addressing system. So the big takeaway here is that TCP prepares the message, and IP ensures it actually gets delivered to the correct numeric address on the network. Now, you might be wondering, what is the absolute smallest network you can possibly have? Well, it's a single-node network known as localhost, and it's assigned the internal-only IP address of 127.0.0.1. If your computer wants to communicate with a service running on its own hardware, like, say, a local print server, it addresses itself using this localhost IP. It's basically the machine talking to itself in a mirror. All right, let's jump into Section 3, building a basic network. Let's look at a really practical micro case study from Red Hat to see how this works in the real world when you don't have automated systems holding your hand. Imagine you just have 2 computers and a single crossover Ethernet cable connecting them directly. No router, no external network, just you. Step 1, you have to discover the network interfaces on both machines using the command line. Step 2, you manually assign static IP addresses to each machine, and you typically use the 169.254 block, which is reserved for self-assigned IPs. Step 3, you explicitly set the network routes so each computer knows exactly where to send its data. And finally, Step 4, you use the ping command to verify that the connection is actually alive. Now, obviously, that manual setup is fantastic for learning, but it absolutely does not scale. In the real world, you are rarely going out and assigning static IPs manually for every single device. Instead, a dynamic host configuration protocol, or DHCP server, automatically assigns and tracks IP addresses as devices join your network. But, and this is important, as a sysadmin, understanding that static manual process gives you the critical foundation you need to troubleshoot when those dynamic systems inevitably fail. Which brings us to Section 4, managing network interfaces. Let's shift our focus to the terminal and see how Linux categorizes physical hardware. The ArchWiki has this great breakdown of predictable network interface names, and it honestly takes all the guesswork out of hardware identification. When you list your interfaces, you aren't just seeing random strings of text. A prefix of EN means it's a wired Ethernet connection, WL indicates a wireless local area network, and WW means mobile broadband. So just by looking at the first 2 letters, you immediately know exactly what kind of hardware you're dealing with. It's one of those great aha moments when you realize just how intuitive it is. Quick heads up for anyone jumping into this today, though. You need to be aware of a major shift. The older networking commands, which were bundled in a legacy suite called NetTools, have been deprecated in systems like Arch Linux. So aspiring sysadmins absolutely must rely on the IP Root 2 suite as the modern networking standard. If you've been trying to run legacy commands and they just aren't working, well, this transition is likely exactly why. So using that modern iProut 2 suite, you're going to rely on commands like iplink set, followed by the name of your interface, and then up or down. This is basically the software equivalent of physically plugging in or unplugging a network cable. Right from your terminal, you have total control to physically enable or disable a discovered interface at will. Okay, so our interfaces are up and running. Let's move to Section 5, Routing and Troubleshooting. To send data anywhere outside your immediate local network, Linux relies on a routing table. Red Hat uses this really great metaphor. They call it a city map for your network. Using the IP route command, you can view or actually build out this map, giving your operating system explicit directions on the path traffic must take to get from point A to point B. Because without a properly configured routing table, your data literally has no idea how to leave the computer. But what happens when that data fails to arrive? Because eventually it will. That's when you turn to your troubleshooting tools. The classic one is ping, which sends a simple echo request just to test if a host is fundamentally reachable at all. But let's say a machine is reachable, but a specific service on it still isn't working. That's when you need a deeper tool like SS, which is part of that IP Route 2 suite we talked about. SS lets you investigate detailed activity on specific TCP or UDP network sockets, so you can see exactly what ports are open and listening. Here is a really fascinating edge case from the Arch Wiki, though. Sometimes the problem isn't actually your machine at all. Linux uses a feature called window scaling, defined by RFC 1323, to send larger amounts of data way more efficiently. However, some broken hardware routers out there on the internet will maliciously rewrite this scale factor to 0. This causes connections to just drop entirely or crawl to a halt. It just goes to show that even a perfect, flawless Linux configuration can be broken by external hardware, meaning the sysadmin has to manually go in and disable the scaling feature just to keep traffic moving. And that brings us to our final section, the enterprise advantage. Let's zoom back out for a second. Why do businesses actually care if you can run an IP route command? Well, because mastering Linux networking is what enables you to handle massive enterprise workloads. As IBM points out, Linux underpins major cloud computing platforms, running these massive KVM hypervisors. It's literally the foundation for containerized DevOps, efficiently routing traffic between microservices. And it provides enterprise-grade security through advanced firewall configurations like IP tables. Seriously, if you know Linux networking, you kind of hold the keys to the modern data center. Which really just leaves us with one final thought for this explainer. With Linux powering literally everything from the smartphone in your pocket to the entire global cloud infrastructure, the question isn't really whether you'll eventually need to manage a Linux network. The real question is when. I highly encourage you to go spin up a virtual machine, open a terminal, and just start experimenting with these concepts today. Thanks so much for joining me and happy learning.